Log on, tune in, find out. Another good idea from Cambridge.
Zelevinsky here, talking about cluster algebras and quivers with potential.
Thanks for the invitation. It's always a pleasure to be here. So when preparing for this talk, I realized that probably the title is too ambitious and I will not have much time for quivers with potentials. Probably they will appear only at the very end. Also because I want to kind of justify or try to justify my appearance here, what this all has to do with algebraic Lie theory. So I'll try to concentrate more on this part. Well, I will not do the usual sales pitch about cluster algebras. They already were around the block for some time. So let me just start by introducing the first one of the main ingredients. And the first ingredient is purely combinatorial. It's the notion of matrix mutation. So we deal with n by n integer matrices. And most important for me would be the case when this matrix is skew symmetrizable. Which means that di bij is minus dj bji for some d1 through dn positive numbers. If all d's are equal to 1, you get skew-symmetric matrices. And this is some kind of discrete data which you think of as some kind of analog of symmetrizable Cartan matrices that you need to define Kac-Moody Lie algebras. So there is relation on several levels. But here the important difference is that it's not enough to just consider one such matrix, but it has to be changed in the process of constructing a cluster algebra, and this change is given by the notion of mutations. So for any matrix index, we have this notion mu. We have this transformation mu k that transforms B to another matrix of the same kind, given by completely explicit formulas. B prime ij is minus b ij if I equal to k or j equal to k. This k is given, so you in the row and column labeled by k, you just change the sign. And otherwise, you do the following. You take bij plus bik plus times bkj bracket plus minus bik plus times minus bkj plus, where this bracket plus function is b plus is defined to be maximum of b and 0. So this second case can be written in many equivalent forms. Instead of this plus function, you could use absolute value. And this is a funny operation. One checks easily that First of all, it's an involution. When you apply this operation again, you return to where you started. And second, that it preserves skew symmetrizability. Actually, with the same choice of those factors di's, which makes it really a very simple check. And the first property allows you to introduce the equivalence of matrices. Since when you apply it 2 times, you arrive where you started, you can define the mutation equivalence. So 2 matrices will be mutation equivalent if one can be obtained from another by a sequence of mutations with varying case. Okay? Well, this notion was introduced by Sergei Fomin and myself from the start. It's one of our main kind of ingredients of this cluster machine. And after a few years, we realized that it appeared practically at the same time in the work of physicists, exactly the same formulas, the same notion appeared in the theory of Zeiberg dualities. And now, of course, it also has many other kind of categorifications, many other interpretations, this matrix mutation. But one can look at it combinatorially. Already on a combinatorial level, there are some natural questions. Let me mention 2 of them. Let's say that B is of finite type. If in the process of mutation, you will never reach the situation when the product of 2 opposite entries goes beyond 3. So let me see, if B prime ij times B prime ji always stays below 4 for any B prime mutation equivalent to B, and of course for any I and j. This looks at the moment as somehow not very motivated. Why 3? But it will become clear why this condition is important. But still, one can already kind of pose the question of classifying mutation equivalence classes with this property. And the answer is very attractive as part of Sergei and myself classification of cluster algebras of finite type. So there is this theorem. Proved in Cluster Algebra 2 paper. There is a series. And it says that the mutation class, a mutation class of skew symmetrizable integer matrices is of finite type. If and only if it contains some B in it. Its Cartan counterpart, which I'll define at the moment, is a Cartan matrix of finite type. So the usual Cartan matrix that corresponds to if its not necessarily indecomposable, then it corresponds to the disjoint union of finitely many Dynkin diagrams. So, and A of B is given as follows. The most naive way to transform this skew-symmetrizable matrix into a Cartan type matrix is this. We need to have 2's on the diagonal, and we have minus absolute value of Bij of the diagonal. So clearly then it's Cartan condition, and it becomes symmetrizable. And we just, it turns out that to achieve this condition, that under any mutations you will never go beyond 3, it's completely equivalent that after some mutations you hit a matrix that after this simple transformation becomes one of your familiar Cartan matrices. And moreover, this correspondence really gives you a kind of one-to-one classification. So this gives this kind of bijection, finite type mutation classes versus Dynkin diagrams.
Are the other B's computable from the Weil group? Are the other B's the other A B's computable from the Weil group?
From the Weil group of what?
Of the Cartan matrix?
Oh, that's a very good question. Yeah, actually, the answer is yes. One has to be more precise. Yes, the answer is yes. So in another paper with Mikhail Barot and Christoph Geis, we kind of solved what could be said this recognition problem. Suppose you have a matrix B, how to just look at it and decide from without performing any mutations whether it will be in such a mutation class. And you're right, they can be characterized by the property that properly defined Cartan companion, so to say, becomes the Gram matrix of some finite subset of the root system.
But translated part.
Not exactly translate, but something more, no, not translate, but something more complicated. But you can characterize it exactly in terms of the root system. That's true. Okay. And here, there is more, of course, hidden here. For example, when A is given, there are more than one B's corresponding to a given A, because we still have to follow the distribution of signs in the opposite, how this plus and minus sign gets distributed in the matrix B. But it turns out that it does not, in this classification, it does not matter. Once you fix the root system, once you fix the Cartan matrix, then all these different choices of signs will be mutation equivalent to each other. They correspond, in fact, to different orientations of the Dynkin diagram. Okay? So this gives you an honest classification and tells you in particular that if your matrix is of finite type, the notion of a type is well defined. You can say D4 cluster mutation classes and so on. And let me briefly mention another classification problem which was solved only very recently. In a sense, from this point of view, it's more natural. You can just ask, how do you classify mutation finite matrices? Those matrices that after you apply mutations, you get finitely many. In other words, that the matrix entries stay bounded, that they don't explode. The classification becomes much trickier. Only this year it is proved. It has The answer is kind of interesting and not very well understood. These are, and by the way, only for the skew-symmetric case. In general, such a classification is not known yet. It's a nice combinatorial problem. But even for the skew-symmetric case, the proof, the result is due to Anna Felixson, Pavel Tumarkin, and Mikhail Shapiro. And the proof is absolutely horrible. It absolutely doesn't tell you why this is true. They use full search whenever possible. And the answer is that there is this natural construction that produces these matrices from kind of topology, Riemann surfaces with finitely many marked points. And besides those, there are only 11 exceptional finite mutation types that do not come from Riemann surfaces. So that's a completely different story.
And when you say that, you mean non-integer entries? What are we talking about?
No, integer entries.
Oh, this is in integer.
Only integer. We never consider, no, only integer.
These other guys, these fellows you just mentioned, they're talking about integer.
They also have integer entries, yes, absolutely. So in this work by...
So what's the condition that the entries don't blow up, or what did you say? I don't understand the difference between this condition.
Well, one can prove actually that in order not to blow up, one needs the condition that this product never rises above 4, not 3. But there are some cases where the product stays, achieves 4, then they will not be of...
Orbits that,
Yeah, finite orbits, but not obeying this 3 condition, kind of this 3 in the right-hand side. There is no a priori reason if you just look at this problem and know nothing else why it should be 3. A more natural question
Can
is...
you even say it's linear growth, like Kac-Moody algebras?
There are results in this direction, yes. Not I think, final, but yes. For example, all affine types have this mutation finite property. Okay? Okay. Now let me move from combinatorics to algebra. Let me define or recall the definition of cluster algebras. In a special case, which will be sufficient, what we call cluster algebras of geometric type. And it goes as follows. Now we fix 2 numbers, m greater than n, 2 positive integers, and we take integer m by n, so rectangular matrix, which I will call B tilde, which will look as follows. You think about it as consisting of 2 blocks, n, m minus n, and n again. So the top block, n by n matrix, will be just as before, skew-symmetrizable. And there are no conditions on the bottom part other than that they're integers. Okay? So a little bit more degree of freedom added. And to each such matrix, we associate this commutative ring, this cluster algebra of geometric type. It will be realized as sitting inside the field of M. Sitting inside the field of rational functions in M variable. M is the number of rows. And it's defined as follows. So first of all, we take this initial kind of set of independent variables. We split it into 2 parts. We take the first n, and we call this collection the initial cluster. And then we take the rest, and we call them frozen variables or frozen generators. And the cluster algebra is defined by some kind of recurrence process, which will kind of change the elements of these clusters, but will leave alone, will never change these frozen variables. They will be fixed during the whole recursive process. So the pair B tilde in this cluster is called the seed or initial seed. And our cluster algebra will grow from this seed. And the main notion here is the notion of seed mutation. So we take this seed, which produces new rectangular matrix and new cluster, and the new matrix is obtained by just matrix mutation of the original one. And you could say that I never defined the mutation of rectangular matrices, but actually these formulas make sense. So this mutation of rectangular matrices is defined by the same, absolutely literally the same formulas as here. And the new cluster is obtained from the old one by removing one of the elements, namely the one corresponding to this k, and exchanging it with something else. And this something else is a rational function given by the following relation explicitly. Here you write xi b I k plus another product, I from 1 to m again, xi to the power minus bik plus. So in the denominator you have this cluster variable that you replace or exchange, and in the numerator you have the sum of the products in your cluster. I mean, you look at those exponents, it's actually very simple. You look at the kth column of your rectangle matrix, and you kind of separate positive, you look separately at positive and negative entries, and you use positive entries as exponents in one term, and negative entries, or rather their negatives, as the exponents in the other one. So this matrix serves pretty much for encoding these exchange relations. Okay? But what is important that after performing this mutation, we arrive at a different place, and we can repeat this procedure. And now the new exchange relation will be dictated, these exponents will be dictated by the new matrix at this form. And then we kind of continue, and oops. Becomes a silent movie from this point. Okay. Well, again, one can check very easily that this mutation of seeds is an involution. If you apply this operation to the new one, you return back. So it allows you to define the notion of equivalent seeds in the same way. And then you define this fancy X to be the union of all clusters obtained from the initial one by a bunch of mutation. Take all the cluster variables that are obtained by iterating these exchange relations. These elements are called cluster variables or cluster generators. And you define your cluster algebra you use as a ground ring. It's convenient to work over Z. You use this as a ground ring, the Laurent polynomial in the frozen variables. And then you just generate the subalgebra inside your ambient field. The subalgebra generated by all these cluster variables. That's the definition. Well, at the first glance, of course, it's not clear why this definition makes any sense. In general, you can imagine that when you perform these mutations in all directions, you generate infinitely many, or even exponentially many, cluster variables. So this will be a very hard to handle. But it turns out that there are many interesting cases when this growth actually is restricted. And in particular, one can now define a very natural notion of the cluster algebra of finite type. Simply if, by some miracle of nature, this process of repeating these exchange relations in all directions only results in finitely many new rational functions. Hard to imagine that that's happening at all, but now a theorem, also by Sergei Fomin and myself, also proved in cluster algebra 2, tells me that A of B tilde is of finite type if and only if this B, the top part of your matrix, B tilde, is of finite type according to this combinatorial definition. And in particular, combining this result with the previous one, we see that cluster algebras of finite type have the same classification as semi-simple Lie algebras and many other things. They're classified by Dynkin diagrams.
Finitely many variables, is that the same thing as saying it's finitely generated as an algebra?
No, it's not the same thing, no. Obviously, it's through one direction that all such guys are finitely generated, but not the opposite. And in fact, as far as I know, the problem of classifying all cluster algebras finitely generated just as commutative rings is still completely open. We do have some sufficient condition for this, which covers many interesting cases, goes beyond this finite type, but it's only yes. Affine types will also fit. They will satisfy the sufficient condition, but there are cases when it's not true apparently and the criterion is not known. Okay. Now, again, there is another difference between this theory and the theory of Kac-Moody algebras, that in Kac-Moody, once you know your Cartan matrix, you're done. There is only one Kac-Moody algebra. Here, the role of your Cartan matrix is proved by this B. And the general principle is that all the important properties depend on B. But there is this additional degree of freedom, this bottom part, which is, we think about it as the choice of coefficients in your exchange relations. You see these guys, these frozen variables appear in those products. The products goes all the way down. So there are those frozen variables that appear here, but they will never appear kind of on the left-hand side. They will not be exchanged by anything. They will just stick there, and they will only give you this ground ring here. And different choices, even for a given B, different choices of these coefficients give you meaningful kind of different realizations of your cluster algebra, and they will not be isomorphic to each other, and if they are realized as coordinate rings of some interesting varieties, the varieties will be different. But this shows that kind of combinatorially, the structure is really, the underlying structure is really the same. The differences are on some kind of more superficial level, one could say. Well, how do we deal with this kind of difficulty that there are many different systems of coefficients? It turns out that there is one more equal than others, and this is called principal coefficients. And here the choice of B tilde is completely prescribed by B. So here M is 2n. And you put this bottom part to be just the identity matrix. And instead of, in this case, it's even convenient to rename frozen variables y1 through yn rather than xn plus 1 through x2n. This turns out, it's not clear from the start, but this turns out to be the most important and in some precise sense universal choice of coefficients. So the corresponding algebra let me write, it actually depends on B, on the top part. The bottom part is prescribed. And once you know this one, you will know any other, and in some precise sense, which I don't want to explain now. So the problem is how you think about these algebras. This is a well-defined algebra, and here it's natural to ask the question how these cluster variables are parameterized and how we can compute them. And maybe you heard that there is this Laurent property in cluster algebras, which says that every cluster variable, although by the exchange relations it only prescribed to be a rational function, in fact is a Laurent polynomial in the initial cluster. But now we can strengthen this property. Let me state this theorem, which I prefer now to call strong Laurent phenomenon, also due to Sergei and myself, and it's stated as follows. So in this A bullet of B, every cluster variable Z, which sits in this fancy X, has can be written uniquely in the following form. You write Z, and you write it in terms of your initial cluster, x1 through xn. And first you write certain monomial, x1 to the g1 xn to the gn times fz. Let me write and then explain. U j y j hat for some integer vector of exponents in this monomial. And then f is supposed to be also depending on the choice of my cluster variable, is a polynomial, honest polynomial, not Laurent polynomial, in n independent variables. But here I want to substitute, to plug in for each variable yj, this yj hat, which is simply given as follows. Yj hat is yj times the product from 1 to n xi to the power bij. So it's a simple monomial substitution into this polynomial.
Without any pluses?
Nothing, just like that.
So negative?
Yeah, here you could have positive and negative. This is Laurent polynomial. And when you plug them in, f is an honest polynomial. So the result of this, when you expand in terms of the initial cluster, you get the Laurent polynomial because of this negative exponents. But this is stronger. It tells you that the Laurentness is really the result of this pure polynomial thing and this monomial substitution. And these g's also, some of them can be negative.
So the y's are the frozen variables.
Hmm?
The y's are the frozen variables.
Yeah, the y's are just the frozen variables, yes. Yeah. Then when you look at this theorem, you realize that everything you need to know will be determined if you know how to compute this sequence of vectors, this dynamics of vectors, integer vectors, and this sequence of polynomials. These guys are called, not very imaginatively, G vectors. And this we call F polynomials, yes. You got the drift, yes.
Oh, it was at your another talk.
Hard guess, yes. It turns out also, I will skip this part, but it turns out that I stated the theorem in this algebra with principal coefficient, but there is a very explicit, very precise formula that once you know these G vectors and F polynomials, then you can compute all cluster variables for every choice of coefficients. So this is really the most important things to determine if you need to have complete control over your cluster algebras with varying coefficients.
So for every z, you have one of these f of z.
Yes.
So the same and a g of z.
And the way it goes, I prefer to think about it as follows. Gz, this integer vector, is kind of used for parameterizing your cluster variables. So you first compute your G vectors. I will show you the example in a moment. And then you use them for kind of distinguishing cluster variables from each other. They will be parameterized by these integer vectors. And for each integer vector, you want to compute the corresponding polynomial.
And this b is a finite type for this theorem?
No, this theorem is completely general for arbitrary b. But what I want to do now, as I said, to justify my presence here, is to give you a new, relatively new theorem of last year, proved by my graduate student Shiwei Yang, where we give for finite type a kind of uniform, not case by case, but uniform realization of this principal coefficient cluster algebras, which I think is interesting. Now let me see. We fix this Cartan matrix A and fix the corresponding root system. So Aij, as usual, is alpha I check alpha j, or is coefficient of omega I in the expansion of a simple root alpha j. This we fix. Now we want to take some b such that this Cartan companion of b is our fixed matrix. And we have this additional degree of freedom. And it amounts to orienting the edges of your Dynking diagram. But it's more natural for us to replace this choice with the choice of a Coxet element. In fact, so choices of b completely one-to-one to choices of a Coxet element. Let me write C equal to SI1, SIN, some permutation product of all simple reflections in some order. And how, given C, we define this matrix B? Very simple. We write I precedes J with respect to C if Aij is non-zero, and indeed Si precedes Sj in C in this product. And once we fix this Coxet element and we have this preceding relation, we define Bij to be, here I have to be, so it's minus Aij if I precedes J, Aij if it's other way around, if J is before I, and 0 in all the other cases. Actually, you might just say that you can use any of these formulas because the other cases is when Aij is 0.
We can drop the condition on Aij being 0 in the definition.
Yeah, because otherwise you can exchange them and leave the Coxet element without the same. I want it really to be one-to-one. Yeah. Now, our construction is simply this. We have a root system, we fix some Coxet element, and we want to introduce an algebra, build a commutative ring that will be naturally isomorphic to this cluster algebra with principal coefficients. And I'm fortunate that the previous speaker actually introduced pretty much all the definitions I need for this construction. Unfortunately, they are not on the board, but I will use them. Okay, so now we fix A and C. And consider all the usual players corresponding to A. Simply connected with semi-simple algebraic group over complex numbers. Let me just work over complex numbers. Well, B, T, U, B minus, N, W all have the same meaning as in the previous lecture. B is Borel, T is maximal torus, U is unipotent radical of B, B minus is opposite Borel, N is the normalizer of your torus, W is the Weil group. And also we have this lift that was kindly defined. Actually, for my purposes, I use SI or to be this phi I of something specific. In the previous lecture, it was any t. Let me just fix it this way. Well, now, having all this in our disposal, we can define some decomposition that is kind of, at the first glance, extremely close to what was described in the previous lecture, to Deodar's decomposition, but in fact it's different. It is something that De Concini and Procesi studied, what we call double Brouwer cells, and then Lustig used them in his study of total positivity. So double Brouwer cell the only little difference is that you have B minus on both parts here and B on both parts here, but this already has this consequence that nothing acts. So you can't factor on B and you can't push it forward to the flag variety. So it's a more complicated class of varieties. And it's kind of funny that in a paper, in an Invenciones paper with Arkady Berestyn some years ago, written for completely different purposes, we realized that it's technically convenient to kind of reduce these double cells a little bit, and you do it as follows. That U intersected with the same thing. So this is this little reduction. This we call reduced double cells. And now let me state one of our main results with Chevret. So theorem. There is a natural isomorphism. This principal algebra, okay, for purists, purists we take complexification, is naturally isomorphic to the coordinate ring of this particular reduced double cell. Remember, the Coxeter element is fixed, and this is exactly what is used here. And under this isomorphism, the G vectors, those vectors that will parameterize your cluster variables, can be described as follows. So first of all, we identify the Zn, where they're supposed to live, with the weight lattice. Using fundamental weights as a basis. Now, every G vector is supposed to be a weight under this identification, and then we say that those G vectors are vectors gamma, weights gamma of the following form. You take some fundamental weight, and you hit it with the power of your Coxeter element, but there are additional conditions in this M, which are as follows. You start from the beginning, you start hitting it with your powers of Coxeter, and you keep going down in the natural partial order on weights. So the difference each time is a sum of positive roots. And you have to stop on the downhill when you keep going downhill. Eventually, if you will do it many times, it will start going up. But you don't take those. You only take those that you encounter on your way down. So there is...
Is M half the Coxeter number?
No, M is some kind of relative Coxeter number. It depends on the choice of I. So you have a bunch of relative, I don't know.
They're different for each I.
Yes, they are different for each I, and there is a nice, completely explicit answer recipe that allows you to compute them. I think of them as some kind of relative analogs of half Coxeter number, because Coxeter number would be going all the way.
Yeah, but then it would be independent of I.
Sure, that's why, yeah, it's only some kind of analogs. I think the average overall I is probably half, I don't remember now, is half the Coxeter number. Yeah, but yeah, there are nice recurrences that allow you to really, you have complete...
Does M depend on C, or is it just...
Yeah.
M depends on the...
So this distribution of these M's as functions of I depends on the choice of Coxeter. For different choices of Coxeter...
M depends on I and C.
Yes. And this is the condition, yes. And you have to say what are F polynomials, but this requires too much preparation. So let me instead just tell you what are the cluster variables in this realization. Right? If you identify the ring itself with the coordinate ring, you can identify cluster variables with some functions on your reduced cell. And then we say that Z gamma, so the cluster variable whose G vector is gamma, where this thing is, let me say, principal generalized minor. So how you think about these functions? Gamma lies on a W orbit of some fundamental weight. The corresponding weight gamma, you think about it as some extremal weight of the corresponding fundamental representation. You can consider the representation itself, and you can compute the matrix entry the kind of diagonal matrix entry corresponding to this one-dimensional weight space. And this matrix coefficient will be this function delta gamma gamma.
By B.
Huh?
By B.
Oh, principal because kind of the set of rows is the same as the set of columns. For type A, this is honest rows and columns, and they should be the same. That's why I call them principal. You could define this delta gamma delta for two extremal weights, and that's what we do. But here, there's this principal thing.
Does it correspond to a vector in the representation transported by C?
Not by C, it's,
By C to the n.
yes.
Yes.
So you take this weight, you consider it as an extremal weight in your fundamental representation with the highest weight, omega I, and you consider the action of your group G in this representation, and then you write it as a matrix and take the matrix entry that corresponds to this one-dimensional kind of weight space. Actually, the normalization does not matter because it's kind of still the same vector. So this is uniquely, it's well defined. So that's it. Yeah, you can compute it quite explicitly for other types, but that's what it is. And in fact, you can use this for doing this computation of f vectors. Once you know this specific realization, it's not difficult to compute the f vectors. And in fact, it's also this f vector in u1 evaluated for arguments u1 through un is actually the value of this same determinant or generalized determinant with some product of elementary factors in the group, which I don't have time to write, but this is all in our paper. So everything is completely controlled here.
So you're moving through the extremal vectors, or some of the extremal.
Some of them, only some of them. Only these guys, and only they correspond to cluster variables.
So why is that? I mean, is this
I don't have a choice.
general choice of,
No, I don't have a choice because, you know, I have my general framework. I know.
you could maybe extend the framework
I don't know.
to the Coxeter element.
I don't know, but here this is a well-defined problem. Cluster variables is not something I can change at this stage. I want to compute them, and here are they all.
You could instead of having B, you could have something more that would cover not just a Coxeter element, but something.
Well, I could, and this probably would be some other notion other than just this one. Okay, let me just conclude by saying that in this cluster algebra 4 paper where we introduced all these G vectors and F polynomials, we gave a bunch of conjectures about them. All of them can be stated incredibly elementary. Let me just give you one sample. There is a constant term conjecture that F polynomials have always constant term 1. And all, for some reason, for us at least, turn out to be incredibly hard to prove. So this particular realization makes it obvious that this conjecture, this, for example, constant term and other conjectures are true for this class of algebras, but this is, from our point of view, a very small subclass because you only have finite type and many interesting, and the conjecture is completely general. In general, we have to do something else because in general we don't have such an explicit realization, and this is where this quivers with potentials come into play, and we use them in this recent work with Harm Dirksen and Jerzy Weyman to give a different interpretation of F polynomials and G vectors using representation theory of these quivers with potentials. I absolutely can't say a word about it. My time is over. But it allows you also to prove this, for example, constant term conjecture and others in much more generality, but only for skew-symmetric matrices. As far as I know, even this constant term thing, which is defined for you, is open for an arbitrary skew-symmetrizable thing. Here, this approach does not make any difference between skew-symmetric and skew-symmetrizable, so for finite type, it's true. It's true for all skew-symmetric using these quivers with potentials, and that's as far as we can go at the moment. Well, thank you for your patience.